Girder will do the first half, and then Elena will do the second half.
We're going over curved girders today. Outline for our slideshow is what is a curved girder. We're going to go over the UT programs. There's two of them, UT Lift and UT Bridge. And we're going to give you some examples that we've done here at Siefert. First, what is a curved girder? So, the NHI specs consider when you have a central angle of your girder is less than 3 degrees, you don't have to consider it curved, which is helpful because there's a lot of extra work that goes into analyzing curved girders. There's also an ASTRA spec that considers it 0.06 radians, which is a little more than 3 degrees, so you have a little more wiggle room. But the central angle of your girder is the arc length of your girder divided by your radius. So normally you have to have a very large radius in order for it to be considered a straight girder, and I haven't come across this in any of the curved girder jobs I've done, but I think other people have at Siefert. So if you meet this criteria of being less than 3 degrees, you don't have to consider its curvature, and you can analyze it as a straight girder as you normally would. So how do curved girders behave differently? Their center of gravity is on the inside of the curve, which is something you don't have when you're analyzing straight girders. This can cause tricky rigging situations, and you really need to look at different spreader bar lengths and different rigging options when you're looking at curved girders. Here's an example of a curved girder being set with a crane. This is the Glacier Skywalk in Jasper National Park, Canada. I almost went to this on vacation, but it was very rainy and snowy the day we were going to go, and we didn't end up going. But found some pictures online. Another aspect you want to look at is twist of your girder. So this is what can happen when you have curved girders and you fix them up. They can twist a lot. The twist is caused by the center of gravity being inside your radius of curvature and your pick locations not in an ideal location. Your girder can be considered stable while still rotating, so it's something that we really need to look at when we're giving our packages to the clients, that they're not just stable and they have a minimal twist. So when you're making your girder connections to splice plates, they're easier to make if they have less twist. So one of the UT programs we use to look at curved girders is UT Lift. UT stands for the University of Texas, which is where it was made, and it is an Excel template that looks at curved girders on the hook. It's a very handy program, and it's very user-friendly, and it has a lot of different functions. It can tell you your center of gravity of your girder, which is nice. It gives you your ideal lift location. The image in the top right corner shows your ideal lift locations where your line of support runs through your center of gravity. This is nice because you have zero twist in your girder when your line of support runs through your pick points. And your reactions will be equal at both pick points. The image in the bottom right corner shows when you can use any length spreader bar in UT Lift. So when you use any length spreader bar, your center of gravity might not be located at the line of support, and you'll have an eccentricity, and this is where you get your twist from in your girder. UT Lift lets you put in any size spreader bar you want, and you can look at the different stresses along your girder and your twist. UT Lift looks at stresses in the top flange, both sides, the right side, left side, and stresses in the bottom flange, right side, left side, at several points along your girder, The bottom image on the screen shows it taking 5 sections in the beginning of the girder at your first pick point, in the middle of your girder, at your second pick point at the end of your girder. So it looks at stresses throughout the girder, not just in one location. I'm going to pull up an example of a UT program. So this is UT List. Whenever you open the program, you have to click on the icon that says Enable Editing and able to allow the program to run different stresses when you change the input. So this is the cover page. The University of Texas created UT List program. This is version 1.3. They're always coming out with new versions and updates to it, which is very helpful, and you can find information online about it. Your first page is your input page. It's pretty straightforward, where all of your green boxes are your inputs and all of your blue boxes are your results. So title it, project name. This example is Unit 1 from the Whippin Bridge that I worked on with Kevin. I was looking at girder G4E. You can input how many sections along your girder you have. So this is helpful when your girder is changing cross sections along it, or if you have 2 splice girders that have different cross sections, different plant thicknesses, you can take that into account in UT List. So you input your section properties, top flange, your web, bottom flange, your length along each section, and your radius here. On the bottom page of the Input tab, you have your crossing setup. UT List does a nice job of explaining all of its inputs. If you hover over the box, it'll tell you what you should enter. And it has a nice diagram on bottom of this is your cross frame location. So this is the length along your curve to the cross frame number 1. And your distance S is the length of the cross frame. So you can put cross frames on the inside of your curvature, the outside of your curvature, or both the inside and the outside, which is typically what we see when we're doing rigging and calling out our diagrams. So to input the diagrams, you can use the constant buttons up top if everything is spaced evenly in the same weight, where you can put in one weight and hit constant crossframe weight for all of them. If you have in, let's say, 5 crossframes, it will pop out all of your same weights down here. And then you can choose your spacing, set it at 10 feet, and hit constant crossframe spacing, and it will automatically put in your length for you. In this case, I had different spacing in between my crossframes, so I did it manually. So after you've inputted all of your section properties and your crossframes, you can look at your outputs. So first output tab is your center of gravity and your ideal lift point. It tells me my total length and weight at the top, and then my distance along the curve to the center of gravity. It also gives me the offset, which is the distance from the center of gravity to the edge of to the center line of the girder. On bottom, it gives you your ideal lift points. So this is where we would use if we had a spreader bar length that you can make any size, and you want to lift your girder with no twist, which is the ideal way to lift the curved girder, then you would use an 88.8 foot, a 66.4 foot starter bar, and it gives you your your location along the curve to your lift point 1 and your starter bar length. So in this case, we were using a specific length starter bar. We can't use a 66-foot starter bar. We go to the next tab. Up top, you can input your location along the curve to your first lifting point, and then your starter bar length. The height H is the axis of rotation. We were using the height of the beam clamps because it's the height off of the girder to where our shackles are located, where it's rotating. After you input your starter bar length and your length to lift point 1, you can calculate your twist and stress. This notification will come up that will tell you that you're about to analyze your girder. It takes a moment, your analysis has ended, and now we can look at our results. So here's our twist and stresses based on the locations along our girder that I described earlier at the end, first lift point at the center, second lift point, and at the other end. Gives you your rotation in degrees, and it gives you stress at the top flange left side, top flange right side, bottom flange left side, bottom flange right side. The other tab that UT-Lift shows is your graph of your displacement, twist, and torsion. These are just nice to see how our girder is changing along the length of it. So after we run our UT-Lift program, we get our stresses, we take our max stress, and we use it to check our girder stability. So the red box is where we put in our stresses, and then we check it using critical buckling stress equations from the ASHTO standard specification blue pages. So UT-Lift is a very handy tool, very user-friendly, easy to use, and it's located online. It's available to anyone. It's free to download, and I also saved it on a server in the following location.
Any questions for Shara?
Yeah, I have one.
Good.
I have a question, Fadi.
Go ahead.
How come you guys don't use, I saw there's like a critical moment that kicks out of that UT lift sheet?
So I was reading through the NHI manual, and it goes over how that critical moment is used as if it was a straight girder. So it's not completely accurate, and I know that the UT Lift program can be used for straight girders. You just input your radius as 0, and you can use every other function of it the same way, where you can get your ideal lifting points based on, like, if you have cross frames in a different location that are going to offset your center of gravity. But that is for straight girder analysis. And I don't know why it's not clearly stated in the UT Lift program, but I was reading that in the NHI manual. So that's why we checked the stress using the other critical buckling stress equation.
Thanks.
The output sheet look like what you submit to the client?
They probably shouldn't do that.
Go back.
Because that ASHTO critical buckling stress they use is definitely for straight girders.
We print the
So I would feel more
middle tab. We print all of our inputs,
which is what that kicks out.
our CG and our DLF, and the calculated behavior. We do this to show what we inputted so they can check. We use the center of gravity on our CAD drawing, we have like a table that will normally show your lift point 1, spider bar length, lift point 2, and to show where we got that from, we include our center of gravity. And then the output page for the calculated behavior will show what spider bar length we used and our stresses. And then we normally highlight the max stress, reference it. So we put all that into an appendix.
Can you explain the difference between picking with one crane and two cranes and how you have to make sure the reactions are similar with one crane?
Oh, yeah. Yeah. So if you're picking with one crane and you have a spreader bar or just swings, you want your reactions to be equal. So you have a certain length spreader bar and you're changing your lift location number 1 until your reactions, which are given here, are equivalent, because that's you want to lift equal weight on each swing. So this is for if you're lifting with spreader bar or swings. If you're lifting with 2 cranes, you can have your reactions unequal and it will still run. It will just give you a notification. So if I change my lift point 1, okay, it gives you a warning, reactions that are not equal, valid only to 2 cranes. This is if you're doing a 2 crane pick, and then you can still calculate your twist. And then it will give you your different stresses below. Does that cover it? Okay. Any other questions?
Analyze your girder on the hook with UT lift. You have to check that it's stable in its preferred position. So for this, we use UT Bridge. This is 3D analysis software by University of Texas Austin, and it's designed with construction in mind. And what that means is it's not meant for permanent design. It's meant for analyzing structures in several stages. So it's designed for exactly how we're using it. There's a lot of capabilities in UT Bridge. I haven't used all of them, but just to list some of them, you can model plate girders or tub girders. I haven't gone into the analysis of tub girders, but you can model straight or curved girders. And then you can perform an erection analysis or a desk placement analysis. You can add a holding crane or temporary towers, and with the holding crane, you can input your holding crane reactions. And then you can add fixities, and because this is a 3D analysis software, you can add the fixie as one of 9 points along the cross-section. So for LaGuardia, we added temporary bracing at the piers, so we added a fixity at the center of the top flange. And then, as Sarah mentioned earlier, UT Bridge is always coming out, or Bridge Lift. They're always coming out with new versions, and this is version 2.2. And I know Fadi mentioned that Bomber used a previous version for Tappan Z, and it was a lot harder to use. So I'm thinking that maybe in a couple of years, they're going to come out with some new versions that have more capabilities and are easier to use. And then online on YouTube, the UT Bridge makers have a series of YouTube tutorials that you can use. I think like 10 up. kind of going to go through how to use UT Bridge. If you open UT Bridge, right away you can select plate girder or tub girders. You can start a new model or open an existing model. And something important to note is that you can't go into the file folder and open it straight from the file. You have to go into UT Bridge and open up a file. To start a new model. The first thing that's going to pop up is your features, and this is going to be project specific. So if you have a curved bridge, you can select seat supports, multiple girders, bridge supports, splices, stiffeners. You can add cross frames or K-frames. You can add temporary supports. And then over here you have to select either erection analysis or placement analysis. Otherwise it's going to give you an error. You can have an eigenvalue buckling analysis, point loads, special degrees of freedom. And there are a couple other capabilities here that I haven't looked into. You can add thermal loads, and you can add a top flange uniform load. So you're going to go through and kind of input all of the basic geometry of the model. And if you, lose this, you can always go back and go to one of these tabs, and it will bring you right back here. So you don't, if you have to change one thing, you don't have to go through all of it and keep hitting next. So the first one is the radius of curvature. Even if you have multiple girders with different radii, you're only going to input the radius of the interior girder, so the girder with the smallest radius. And then the model is going to build upon that girder. And if you kind of forget that, if you click this helpful hint tab, it'll tell you. And orientation, this is just depending on how you want to model your bridge. If you want to model it from this support, it's going to be right. If you want to model it from this support, it's going to be left. So just remember how you orient your girder, because it'll change things later on. And then point of tendency, if your girder is straight, and then at some point along the girder will start to curve. We have one of these set of girders on the Guardia, and this is useful. So you can input a point of tendency for each individual one, or you can make it uniform. And then you're going to put in your girder length. And no matter how you orient your girder, girder 1 is always going to be on the left-hand side. So, yeah, like in the tutorial, it had a left orientating curvature, and UT Bridge, they made girder 1 is that interior girder. So even if you have your bridge curving right, and you put in the radius of that smallest one, that's not girder 1. Girder 1 is always going to be on the left. Make some girders to make them 150 so long. And then if you have all uniform girders, you can just put in the length of the first one and then click uniform, and it'll automatically populate. So spacing, this is how UT Bridge comes up with the radius of the other girders. So unfortunately you can't put in varying spacing, but for LaGuardia we just used an average spacing. So steel properties, it automatically has them, but if for some reason you want to change them, you can change them here. So supports, pretty self-explanatory. You're going to put in the location of the supports on all the girders. So if you look down here, you're going to have two tabs. The first one is going to be for your first girder, and the second one is going to be for your second girder. So put in a support at 75 and girders uniform, and it will change that second tab. And then you're going to input the support type. So 1 is for a fixed support, and 0 is for expansion bearing. And if you forget that, you can put the any question mark. The splices, you can put the location of your splices. And then again, click all your girders uniform. The likelihood of you having all girders uniform is probably small. So if you add in stiffeners, I'm just going to put in 3, but you have to put in a stiffener location at every crossframe location. And it has to be the exact same location as when you input in your crossframe. So my suggestion would be to put them in an Excel file, and then you can copy them in. Because even if they're 1 decimal off, it'll come up with an error. So let's see, put in 3. And then the side, so you can choose to put it on the left-hand side of the girder, the right-hand side of the girder, or both. The 3 is both sides of the girder. And so for this, just remember how you orientated it, what's left and what's right. And then you can click uniform side. It will apply to all 3: uniform thickness, uniform width, and all the uniform. So next is you're going to input your cross frames, number of cross frames, we'll make it 3. So if I were to make this, let's say left girder location, if I were to make it 0.6. If you try to click next, it won't recognize it, that even if it's just like 0.1, or it doesn't matter how many decimal points, it won't recognize that it's the same location. You'll be able to continue, but when you go to run the model, it won't be able to run. And sometimes also this is a problem with YouTube Bridge. If you go back, it'll delete all your information. So I just put all that information in, and if there's a problem with it, I think most of the time that's why it deletes it. But the number of temporary supports, again, pretty self-explanatory. We're going to have 1 for girder 1 and none. So here is when you can choose to put a holding crane or a shoring tower. 1 is for shoring tower, and you don't have to put any uplifting force, it'll calculate it for you. And then your holding crane, you're going to select 2, then you have to put in a force. So store and reference point. So here you have to input your mesh size, and so basically what that means is when it runs the model, it will divide the girder into segments the length of your mesh size. So the default is always 18, but if you have a segment that's smaller than 18 inches, you have to change your mesh size to be smaller. So we have our first segment goes between the start of the girder and where we put that support. We put it at 6 inches off the start of the girder, so this has to be a max of 6 inches. And you can make them all individual, or you can change it and then click uniform mesh size. And then you can click all girders uniform. And every time you change something in your geometry, you have to go through and redefine the mesh size. Next, so you can input the cross-sectional profile of your girder. Here it's just showing one, but you can put in multiple sections. So here you can assign each segment a different cross-sectional profile. And so it assigns a cross-section for girder 1, but it doesn't automatically assign a cross-section for girder, so maybe it does. Sometimes it doesn't. But again, this is another thing that every time you change something, you have to go through and redefine elevation. So if you have a girder that has like significant elevation change between supports, you can go through and you can put the elevation of on the left and the right and the inclination angle. So this is your erection sequence, and this took me a long time to figure out, but the number of stages, say you want to erect these two girder lines in 4 steps. I think we split each girder line into 3 different pieces, but the number of drop-in members per girder, so you're going to start off with 1 segment, and then after that first, essentially, step, like start and end location, however many members per girder that you have to drop in would be this value. So for step 1, you're going to have your first girder, say girder 1 from 0 to the splice location at 100. And then for step 2, you started off with that same 0 to 100 for girder 2, but you're going to drop in 1 member for girder 2. So you're going to have to drop in 0 to 100 for girder 2. And then in step 3, you're going to have the same 0 to 100. And then you're going to drop in from 100 to 150. And then for step 4, you're going to drop in that second drop-in number for girder 2. So girder 1 only has 1 drop-in member, but girder 2 has 2 drop-in members. It will run the model if this isn't correct, but you won't be able to switch between, you won't be able to go past step 1. So you won't be able to see the rest of your stages. This is your temporary support activation. We're going to have it active in step 1 and non-active in the rest of the steps. Point loads. You can put in the location of your point loads. You put in the location on the cross section. So if you click this, it'll show you. You can put it at one of each of these minor points, and then this is kind of your direction. So Z is up and down, X is, I guess, perpendicular to the member, and Y is along the length of the member. You put in your magnitude direction. Here you have your combinations for each step. So in step 1, you can put in your load modifiers, and you can activate the weight or the point load in each specific step. This is where you have a temporary support, or if you have cross frames, you actually have to go back because it somehow always skips the question to, I don't know if I click cross frames, but it always skips the question to tell the model when to activate your cross frames. But if you go past it and then go back, it'll pop up. So you click it and then you click run, and you have to save it first. Save it. Okay, well, there was an error, but it'll run, and it'll run for quite a while, so I'm not going to make you sit through that. I'm just going to open a model that I already ran. So when you save a file, it'll create a folder for that file, and your model is going to be in the folder. And then when you view things, you're going to have this export button, and you can export it, and it'll save it right in the folder that it creates. But every time you rerun the model, anything that you've exported into that folder will get removed. So you just have to remember to copy and paste it into like another folder or something like that. So this is what's going to pop up. So this is your first girder, so this is going to be step one. Change the view over here. So this is just your basic geometry. Over here, it's not really easy to zoom in, but you have your reaction, your vertical reaction, your horizontal reaction, and then up here is where we put that temporary brace, and then it'll show you all your stiffener plates. Here and here are your point loads, and right here is where your holding crane is.
The point loads are splices. The extra weight from the splices.
You can switch to your linear elastic solution, and this will give you your displacement. Up here, it'll show you your max displacement. You can scale this if you really want to. You can see your buckling mode shape, and then it'll give you your von Mises stress. And a lot of times, such as this, your stress is going to be localized over where the brace is. So you can go over here and you can see your stress chart, and it'll give you the stress along the member. So each of these dots is the average stress along each one of those mesh segments. So it's the average along the 18 inches, which is why you don't see this maximum stress, because that's just a point load, and the average over those 18 inches isn't that high. Then you can go back to geometry. You can switch and you can see step 2, step 3, step 4, and then you can go through the same diagrams for each one. Then you can see your moment, your stresses. This is moment and shear. This is showing step 1, so you keep having to click refresh every time. So it'll give you the moments for both girders on the same diagram, and then your shear. So unfortunately, there's no real way to export your inputs. So what we've been sending is we export all the diagrams and we mark them up. It takes a lot of time to make the models, or not, it doesn't take that long, but if you were to model a whole bridge, it would take a lot more time than necessary. So we've just been selecting the couple of cases, the worst case scenarios, and modeling those. Also, the more girders you have, the longer it takes to run, and the smaller mesh size you have, the longer it takes to run. Some of the models were taking like well over 20 minutes just to run and go through. So you don't always have that time.
You use this a lot too?
So here we've been using this max stress if it's along the member. If it's local, we attach the diagram, the member stress diagram, and we show them, hey, like it's just a local stress. Maximum is really has to show us in the diagram. And then, much like we did for UT lift, we used the ASHTO stability analysis from the blue pages, and we just checked the max stress against the critical buckling stress for the factor of safety. Just to go over some user issues that I encountered. I mentioned some of them, but one is that you can't really add to a model. Every time if you try and add another girder, you have to re-input all that data. So that's another reason it's really helpful to just save all your input into an Excel file. It's really easy. You just copy and paste. And sometimes the program will crash and you won't be able to open an existing model. So for that reason, if you save all your input data in an Excel file, it takes 5 minutes just to re-input it. So the cross-framing stiffener plate locations, they have to be the exact same. You have to reassign your mesh size and section properties every time you change something. And the order of erection sequence takes a little while to figure out, but and then when you export the image, they'll delete from the folder, and a smaller mesh size will take longer to run. Any questions?
Did you guys? Okay, if you can't, you're exporting the input like every time you do it. So like if you're reviewing it, what are you reviewing? Are you reviewing the exported input file? But how do you know like the model was actually run off of that?
Yeah, that's a great question. So you cannot review inputs, you cannot review outputs. You have to run the program.
You just rerun it. Like,
I rerun it. Actually, Sierra does it. I don't do it. So we make sure the radius is fine, the splices, the sequence, you can tell from the output. And if we see where the holding crane is, you have to rerun it. That's the only way to check it.
Yeah, so it creates this file. The model is somewhere in here, but it'll give you all of these data notepad files, and this is all you get. You just get a bunch of numbers, and then it has an input file, but it's really hard to tell sometimes what the data is actually coming from, so you have to use the program and just go through.
so it's like an independent check. We're re-inputting all the same stuff and just seeing if you get the same info. Is that
No.
what you're saying?
I check her input. Right.
Yeah, you just go through each step that Elena just went through again. Like you open up her existing file and you check it step by step. Like it'll pop up radius of 400. Oh, that's
Oh, I thought
correct.
you said that like erased, like when you went to redo it.
There's an error with it sometimes, but once it's run, it won't.
If you want to add something, you don't want to change it.
I should just keep clicking next.
Yeah.
You go through
Yeah.
all those
Yeah.
spreadsheets.
You go through it individually. Yeah.
So you mark everything, and then when you rerun it, you have to change the next one.
Got it.
I know it's not perfect, but first, it's for free.
Yeah.
Secondly, it's been working out great with us and LaGuardia, and many times they called me and told me, yeah, it rotated as you told us. It's been a great tool. We've been using it. We have so many curve girders, so many different sequences. It's just you need to be smart about what checking, because you cannot check every line and all of them and every sequence.
It's the best tool for curve girders, right?
I've used it at Tappan Z. It was much harder because everything was like coding 1, 0. It was, and there was no question mark. So you had to really know the program to put the input, and it was very successful, and then we're using it now, and hopefully the next time we're going to use it, it's going to be 3.2 or 2.4, I don't know what the next number is, and it's been great for us.
For what? Free.
But
Well, they got
UT Texas, it's
They got grants from the
grants,
federal government.
yeah.
Tom and I met the guy at the Steel Conference, the lead of this, Paul something or other. I don't know his last name. You got his info. He's super excited to help anybody using the software.
Oh,
It's for free. You know.
when we used it first in Tapanzi, Dr. Yura, who wrote the ASC, I don't know, very well-known guy, spent 45 minutes with us on the phone trying to explain to us how to run it. And we will send it the first time. We did not know all these errors. We'll send it to them, hey, it's not running, and they will go through it and tell us what's wrong. And the best thing about this is that Elena and Girder learn it by themselves. They didn't go to training. It's try and error, and they learn it on the job, practically. And that's it.
Did you notice any, with all the different runs you did, did you notice any trends or rules of thumb maybe that came about based on proportions or anything like that that you would recommend as far as if you have a girder of this length, this curvature, this depth, you know, here's your rigging locations, here's what works, here's what doesn't? Or are we still gathering data, I guess?
Still gathering data. I guess it's just everything varies widely based on your radius of curvature. So could have similar lengths and actual properties of the girder, but your curvature is small for one and larger for the other, and it's going to change everything.
So Ron's favorite line, it depends.
Yeah.
Yeah, and you know what we learned too is when we started this spreader bar and rigging, Ilya gave them rigging length of spreader bar for each one to be perfect. And then they said, no, there's no way we can do that. We have only a 40-foot spreader bar, somewhere use it. So we started using it. The stresses were okay, but the rotation was 20 degrees. We did not, we said that's fine. And then we went down one day, and remember Edwin said, why do I want to use the spreader bar? I don't want to use the spreader bar. I told him it's going to rotate. I'm fine with it. We removed the spreader bar from our rigging because he's okay with the rotation, as long as we check the stresses only. And then the day of them picking it, they couldn't set it. And we called them, that's because of the rotation. And now if we tell them 50-foot spreader bar, they'll say, yes, sir. If we tell them 60-foot spreader bar, I will rent one because they lost a shift because of that.
They couldn't wrestle with it.
Yeah, so now we're more confident when we tell them, hey, it's going to rotate. Initially, we're not sure how much it can, if it says 20 degrees, is it going to rotate 20 degrees? We don't know. But it's been spot on. And they learn to listen to us.
Nice adjustable spreader bar.
This is, most probably, they're going to need that in some of the curved ones when we're doing unit L31, unit 4 to 6, if we get it.
Volunteering?
I got a good one.
Hydro spreader?
Yeah.
One question, guys.
Have we looked at what's the difference in stresses using UT bridges versus design guide 9? What is that method? I know we had originally done that and found pretty high stresses in it.
No, we
I know this is a lot more accurate, but it's also a lot easier to use design guide 9. Curious how we compared results.
Lesson learned 2.0.
Just curious.
It's once you get used to it, you'll be surprised that Elena can do the 3 model in one day and done with it. It seems like a lot of work at the beginning, but actually it's not much.